Good day to you from Chem Help ASAP. In this video, we will explore one of the classic organic chemistry reactions, the Williamson ether synthesis. The reaction was reported in an issue of the Journal of Medicinal Chemistry in a collaborative project between groups at the University of Montreal, led by Dr. Marinier, and Bristol-Myers Squibb, headed by Dr. Jason Priestley. The citation is on the following slide, as well as in the description of this video. Here is our reaction. We are converting the alcohol in the starting material, properly a phenol, since it is an aromatic alcohol, to a new ether. In addition to an alcohol, we need two things for a Williamson ether synthesis. One, we need a base. Neutral alcohols are not strong nucleophiles and cannot perform an SN2 reaction. The base deprotonates the alcohol to give an O-, a strong nucleophile. Two, we need an alkyl halide, or some alkyl chain with a leaving group. We have both of these necessities over our reaction arrow. The base is potassium carbonate, and the alkyl halide is benzyl bromide. Let's clarify a couple ideas. First, let's discuss the base. Normally, in a Williamson ether synthesis, you need a fairly strong base to do the deprotonation. Sodium hydride is common. In this case, however, since the alcohol is a phenol, the alcohol is more acidic. A normal alcohol, like methanol, has a pKa around 16. Phenols are around 10 in general. So the scientists found that a weaker, more convenient base, like potassium carbonate, worked just fine. Second, let's look at the halide, benzyl bromide. Benzyl bromide is a fantastic halide for SN2 reactions. Remember that SN2 reactions often compete with E2 reactions because the nucleophile sometimes acts as a base. In the case of benzyl bromide, there are no beta hydrogens for an E2, so an E2 is impossible. That's one less thing to worry about. So our reaction begins with deprotonation of the phenol oxygen with carbonate, our base, and that gives us our O- species. This is our nucleophile for our SN2 reaction. The resulting anion attacks the carbon of benzyl bromide, kicks out the halide, and forms the new ether product in essentially quantitative yield. That is the Williamson ether synthesis. The product molecule was just one of very many structures made by the joint Montreal BMS team. The team's focus ultimately fell to the molecule shown in the lower right of the slide. The molecule is being used to explore and develop new anticlotting agents for the prevention of certain strokes and heart attacks. You can see how the core of our product and the top right is related to the ultimate molecule of interest in the bottom right. In conclusion, this reaction is a nice example of a Williamson ether synthesis, an old organic chemistry reaction that is still widely used to create new and useful molecules. If you are interested in seeing the rest of the synthetic chemistry developed by the Montreal Bristol-Myers Squibb team, then check out the reference. Please subscribe, like, or leave a comment. Take care.